All right, we're going to look at assessing normality. With assessing normality, there are some key concepts. We are going to determine whether the requirement of a normal distribution is satisfied. We can visually inspect a histogram to see if it's roughly bell-shaped. We can identify if there's any outliers, and then we can construct a normal quantile plot. It was discussed in the beginning, but we're going to look at an example of that. Okay. So what is a normal quantile plot? A normal quantile plot or normal probability plot is a graph of points x comma y, where each x value is from the original set of the sample data. And the y value is corresponding to the z-score of that sample data that is expected from the standard normal distribution. So x is the value of the piece of data given, and then we calculate its corresponding z-score. Now, you can use a calculator. I want to quickly discuss that. For a case like this, normally use technology. First and foremost, you put the data in. So type in your data. Up to here, it explains how to type in the data. We've done that already. I'm assuming everybody knows how to put in the data into L1. Okay, you click on stat, edit, clear list to make sure nothing is in there, and then you put a number, enter, enter, enter. You keep on going and you put the data in. Now you want to come up with the stat plot. So press second Y, then press enter, then select on. So this is where we end up when we press on, and then select type item, last one in the second row option. That means you see the type, this is the one you are going to choose, the last one. For data list, you put L1, and basically you can just press enter, enter. You don't have to do anything. The next one does give you XY itself. As far as the mark is concerned, see, you can choose this one, or you can choose this one, or you can choose this one. So if you can see, when the graph shows up, it shows this one. If you chose the second one, it shows plus, plus. That's all it does, okay? So that is up to you if you want to do that. So this is how the graph looks like if you choose what you want to choose as your mark. Procedure for determining whether it is reasonable to assume that sample data are from a population having a normal distribution.
Procedure for determining whether it is reasonable to assume that sample data are from a population having a normal distribution. There's the histogram. Construct a histogram. If the histogram departs dramatically from a bell shape, conclude that the data do not have a normal distribution. Outliers. Identify outliers. If there is more than one outlier present, conclude that the data might not have a normal distribution. Normal quantile plot. If the histogram is basically symmetric and the number of outliers is 0 or 1, use technology to generate a normal quantile plot.
Apply the following criteria to determine whether the distribution is normal. These criteria can be used loosely for small samples, but they should be used more strictly for large samples. Normal distribution. The population distribution is normal if the pattern of the points is reasonably close to a straight line, and the points do not show some systematic pattern that is not a straight line pattern. Not a normal distribution. The population distribution is not normal if either or both of these two conditions applies. The points do not lie reasonably close to a straight line. The points show some systemic pattern that is not a straight line pattern.
In short, the procedure involves, it's a little bit involved. You look at the histogram, you look at the outliers, and you look at the normal quantile plot to see if it's reasonably a straight line, and that's it. So, for example, let's look at this graph. When we look at this graph, it appears the histogram is almost bell-shaped. And if you look at the normal plot, if you will, it appears to be linear. So that's the idea that it shows we are assessing normality, and this must be normally distributed.
Normal. The first case shows a histogram of IQ scores that is close to being bell-shaped, suggesting a normal distribution. The corresponding normal quantile plot shows points that are reasonably close to a straight line pattern, and the points do not show any other systematic pattern that is not a straight line. It is safe to assume that these IQ scores are from a population that has a normal distribution.
Here's another example. It's a uniform example. If we come up with the normal plot, we notice that there is a pattern. By the way, there seems to be a pattern of this thing continues here, something like that. But it's definitely not linear.
Uniform. The second case shows a histogram of data having a uniform, flat distribution. The corresponding normal quantile plot shows that the points are not normally distributed. Although the pattern of points is reasonably close to a straight line pattern, there is another systematic pattern that is not a straight line pattern. We can conclude that these sample values are from a population having a distribution that is not normal.
That's the idea. We are just examining various graphs. Remember, coming up with a normal plot takes a little bit of time. But if we are given that, we should recognize what's going on. As you look at the histogram, clearly it's not normal. It's not bell-shaped. And so right then and there, it's out. If you look at the normal plot, it's not linear either.
Skewed. The third case shows a histogram of the amounts of rainfall in inches in Boston for every Monday during 1 year. The shape of the histogram is skewed to the right, not bell-shaped. The corresponding normal quantile plot shows points that are not at all close to a straight line pattern. These rainfall amounts are from a population having a distribution that is not normal.
We are just examining different graphs, tools for determining normality. We want to explain that. That was discussed as far as the histogram is concerned. We have looked at that, and we've seen some graphs. We looked at the normal quantile plot, and there are advanced methods. I don't want to discuss that. I don't want to go over that, but just to give you an idea, I went over how you can use, at the very least, TI calculator to see whether, for the normal quantile plot, to see if you have a normal distribution or not. All right, so manual construction of normal quantile plot. How do we do that? Because what I want to do, I want to quickly look at one simple example to have an idea how this thing. The first step is to sort the data, ranking them, if you will, from small to large. Here's the second one.
With a sample size of n, each value represents a proportion of 1 over n of the sample. Using the known sample size n, identify the areas of half n, 3 over 2n, and so on. These are the cumulative areas to the left of the corresponding sample values. These values are the cumulative areas to the left of the corresponding sample values.
Use the standard normal distribution software or a calculator or table A2 to find the z-scores corresponding to the cumulative left areas found in step 2. These are the z-scores that are expected from a normally distributed sample.
Match the original sorted data values with their corresponding z-scores found in step 3, then plot the points x, y, where each x is an original sample value and y is the corresponding z-score.
Finally,
examine the normal quantile plot and use the criteria given in part 1. Conclude that the population has a normal distribution if the pattern of the points is reasonably close to a straight line and the points do not show some systematic pattern that is not a straight line pattern.
So what does it mean when we look at this page? So when we come up with the graph using technology, let's say, we can see what's happening here. For example, this is using StatDisk, some statistical software. There were 250 eruptions that is listed. And here's the data. Obviously, when you look at the data, the histogram clearly is not bell-shaped. Normal plot definitely doesn't fit a linear function. This is it, and that's it. You set it up and you observe.
Let's use the display with the 3 criteria for assessing normality. 1. Histogram. We can see that the histogram is skewed to the left and is far from being bell-shaped. 2. Outliers. The display shows that there are 20 possible outliers. If we examine a sorted list of the 250 eruption times, the 20 lowest times do not appear to be outliers. 3. Normal quantile plot. Whoa, the points in the normal quantile plot are very far from a straight line pattern. We conclude that the 250 eruption times do not appear to be from a population with a normal distribution.
Graph tells us what's going on. If we have the rank, they tell us what's going on. So let's look at this very simple example. We are given the following. We want to construct a normal quantile plot for a sample of braking distance in feet measured under standard condition for a sample of large cars. So this is a sample, and those are the x values. What is the y value? You have to calculate their z-scores. How do you calculate the z-score? X minus mu over c, or x minus x bar over s. So for those values, you have to calculate the x bar. That means add them up, divide by size. You have to calculate the s, summation of x minus x bar, quantity squared over n minus 1, and take a root. And for each value, you calculate the z-score. So for example, for 131, the z-score is negative 1.28. For the value of 134, the z-score is negative 0.52, so on and so forth. Now you're going to plot them and see what happens. So here's the plot. X values along the horizontal line, z-scores along the vertical lines. And of course, if you were to use technology that was mentioned, I hope everybody remembers how we do use the technology. And this appears to be a linear function, and therefore it's normally distributed.